Welcome to the recorded lecture for Chapter 10. We're going to be dealing with water resources in this chapter. A couple questions and some thoughts before we get started talking about water resources. My first question to you is, how much water does it take to make 1 cup of coffee? Your immediate answer might be, well, 8 ounces, maybe 6, maybe 12, depends upon the size of the cup of coffee you're going to have. But would you believe it takes 40 gallons? A full bathtub of water to make a cup of coffee? Well, think about where all that water goes, okay? Well, some of it does go into the coffee. Some of it goes into growing the coffee, to washing all of the things, to maybe some hydroelectric power, to cleaning the coffee beans. All of the things involved in the coffee production use a lot of water. Earth does have an abundant supply of water. It is a renewable supply of water, but our water is unevenly distributed. Water isn't everywhere. It would be wonderful if it was, but there are areas that have a lot of water and areas that have almost none. Some people, depending upon where they live in the world, spend more than 3 hours a day just getting the water that they need to meet their basic daily living needs. This is a scary thought and one that I personally can't imagine, but it is true. We in the US, at least on the East Coast of the US, don't tend to think so much about how do we get water. We turn on the tap and there's water. Water for us, we use pretty freely because it's easy to get. It seems to be unlimited in supply, and it's relatively cheap when it's coming from the tap. Maybe even free if you're taking it from a water tap, from a spigot from a water tap and you're not paying for it, then it costs you nothing. We won't be talking about water pollution in this issue, but water resources. The idea of quantity of water as opposed to quality of water. Quality is chapter 11. And you might wonder why we care about water resources. For me, I started caring about water resources when I was a sophomore in college. And, well, really caring about it. I'd cared about it before then, but it wasn't until my sophomore year of college that I'd learned a lot about water resources. I actually took a 3-credit course that was entirely on water resources. And my professor was sharing with us that he strongly believed World War III would be fought over water rights. When I was a sophomore in college, I guess that would have been the year, that would have probably been spring 2001, that semester. Could have been fall 2000, not sure which semester it was, but this was before September 11th had happened and before we were all living in fear of terrorism. But there had been many papers published. There had been people talking about the concept of water as the driving force for the next world war. Whether or not it still is a topic for debate. But water matters, and having access to water is important. We see countries in conflict right now because of uneven access to water. Humans depend on water for our lives. The environment depends on water too. Living things are made primarily of water. The most we can do is survive a few days without water. Our industry and our agricultural groups depend on using large amounts of water. In pollution, we've always had the saying that dilution is the solution to pollution. The idea that if you dilute something far enough, mix it with enough water, it's no longer a pollutant. So all of these things play into the importance of having access to water. One last thing to keep in mind is that water is not equally distributed. There are areas that have too much and areas that have not enough. And hopefully you remember that when we have too much water, at least too much water above ground, it can lead to flooding. And floods are destructive. Too little water? Well, then getting water becomes the focus of your life, the main thing everyone is concerned about. And we also know but too little water is also destructive to life. So having just the right amount of water is important. Hopefully the things on this slide are already things that you're familiar with. You know that water is a unique substance. It's a polar molecule. The concepts of cohesion and adhesion, that it has a high boiling point and a low freezing point, that water becomes less dense as it freezes, allowing things to live underneath the frozen surface of a lake. Water is the universal solvent. All of these things make water unique, and it makes water the perfect medium for our life to be based around. You also are probably familiar with the water cycle or the hydrologic cycle. You need to remember that water is always changing form as it moves throughout this cycle. It goes from liquid to vapor to solid and back again. As water cycles through this system, it is purified. Physical processes, chemical processes, biological processes are all involved in purifying the water, adding minerals and other solutes to it, as the water becomes a solution as it travels through the ground, is what I was talking about, that it picks up small trace amounts of important chemicals. It goes through our soils, through our wetlands, our streams, our lakes, and eventually to all of us. But purification can only happen in a system that is not overloaded with toxins. So we'll come back to that idea of purification in our next chapter. And hopefully you're familiar with all of these steps for our water cycle: evaporation, transpiration, evapotranspiration, dealing with the water vapor leaving surfaces, leaving plants and surfaces. Precipitation, the concept of runoff, as water runs off of the ground surface. Surface waters versus aquifers, which are underground areas of water, where the water is in aquifer situations. We have groundwater, which is clearly water that's below the ground. Infiltration, as water is going to go from the surface down into the groundwater areas. We have water that's held in glaciers, and, well, drought is part of the water cycle. It's not a good part, but it's still part. This is showing you water as it moves from the source zone eventually to the ocean, or a large body of water at least, with water melting from snow and ice in the mountains. It then goes through these small streams, we would call them our primary order streams, and it will eventually move through this source zone that has high elevation differences. It will then go into a transition zone, where a lot of these primary order streams are going to come together and flow together and to create a larger body of water. This body of water will start to move through the transition zone. The tributaries all join it, and it will start to create a floodplain. In this floodplain, it's areas where the body of water may flood. These are the areas of the ground that will become underwater during flood times. But the floodplain is also going to be where your stream or your river is going to be able to move, because water is powerful, and water does not like to necessarily stay where we put it. It likes to make its own boundaries, and it moves back and forth throughout the floodplain. As we move into the floodplain zone, you find that the water has more sinuosity to it, that it is more twisted. It is going to take over a larger area as it moves. As it goes towards the coastline, whether it's the coast of a Great Lake or the coast of an ocean, there'll be wetlands next to it. Deltas will form if you're forming at an ocean or a large body of water sometimes, particularly depending upon the stream flow being powerful as it comes out into a less powerful ocean. And the sediment will become deposited in these areas. As the water moves offshore, it drops out its sediment, the sediment settles down, and the water continues away from the shoreline. Groundwater is something I could talk about for hours and hours and hours and hours, an entire semester, easily. But we won't do that, perhaps thankfully for you, because if we did, we'd have to use a lot of calculus to talk about groundwater. But groundwater is something we really need to talk about because 97% of the world's fresh water is believed to be held in aquifers. And the water in these aquifers can be hundreds to thousands of years old since the last time it's been above the ground surface. About 30% of rain and snow is going to infiltrate into the ground. The water is going to move through the soil surface. It's going to move through the pore spaces. And in areas where groundwater is infiltrating in, you'll find that the pore spaces contain, these are the spaces between the sediment grains, contain air and water. After the zone of saturation, they only contain water because the pore spaces in that area are going to be saturated or filled with water. That's when we start talking about having an aquifer situation. But through the zone of aeration, sometimes also called the zone of transformation, we find that the water is going to be moving through and mixing with air. This area will be very rich in bacteria and other things that will be helping to purify the water as it moves through. We go through the zone of saturation, and this brings us to our aquifers. Aquifers are considered confined or unconfined. An unconfined aquifer is one where the top of the aquifer is at the water table. It is in contact with the ground above it, and it can get recharged directly from the ground above it. It can also be contaminated from the ground above it easily. Confined aquifers are going to be areas where there is some layer of clay or another impervious surface that is going to be between the aquifer and the ground surface, which means you have to go through that to get to your aquifer. Aquifers can only be recharged through specific zones. We call these the aquifer recharge zones. This is where the water is going to get back into an aquifer. And these are areas that have to have a pervious surface over them, because an impervious surface is one that groundwater cannot move through. When aquifers intersect the ground surface, this is how we get springs, where the groundwater just bubbles up from the ground, and if they intersect and the water's under high pressure, that's when we get geysers and large, strong springs. But humans often remove water from aquifers. We do. This is how we get our groundwater. The problem becomes when we remove water from an aquifer and then make the recharge zone for that aquifer covered by an impervious surface. We're keeping our aquifers then from recharging, which means that we're taking water out and not putting water back in. You recognize, of course, that this would be a problem. This image is showing you some of the steps of the water cycle. And here you can easily see that aquifer there. So you can see where infiltration is going to bring water down to the aquifer. There's the zone of aeration and the zone of saturation. And because the aquifer is directly in contact with the zone of aeration, it is an unconfined aquifer. If it was beneath an impermeable layer, like the layer that happens to be beneath it, we would consider that to be a confined aquifer, so if there was a thin layer of clay above it. Now this aquifer is actually a really special aquifer. It's a water table aquifer or an unconfined aquifer, but it would also be considered a perched aquifer, P-E-R-C-H-E-D, because it is sitting on top of an impermeable layer. So the aquifer itself is a pretty thin lens of water. When I first learned about aquifers, one of my professors told me to think about them as lakes that are underground. So if that kind of idea helps you, you can think of an aquifer as an underground lake. This is showing the concept of a recharge zone here, where you can see where the water is capable of coming in and recharging the aquifer. And this deep aquifer is a confined aquifer. It is between impermeable layers. The only way to get water out of it is to go through that impermeable layer. And the well here has water spurting out the top of it, because if you look The well, where it taps into the aquifer, is actually located beneath the level of water in the aquifer because the water table is actually higher than that. So the water is going to make it easy to come out of the aquifer. Some of you, I believe, have mentioned that you use well water at your houses. And hopefully you've never had to redig a well. But at times we have to redig wells because we've gone through years of drought or other times and the water table has dropped. We try to dig our wells in a way that they will be able to withstand drought years, that the wells are deep enough to always reach the water. However, what this graphic shows you is that the water table can vary dramatically between wet and dry years. And if your well doesn't meet where the water table is, you won't be able to draw any water out. So that dry well would need to be redug in order to get down to the water table for those people to then be able to take water from it. So I've mentioned that a lot of our water, fresh water, is tied up in groundwater, but a lot of our water on the earth is salt water. I doubt you have seen pictures like this before in other books, but I love that our textbook talks about the concept of an ocean hemisphere and a land-ocean hemisphere. Because you probably remember learning way back in elementary school that the oceans cover about 71% of the planet's surface. That's a lot of the planet's surface covered by water. Earth really is a water planet in many ways. About 2% of the Earth's surface is covered by freshwater. It's in wetlands, lakes, streams, and rivers. It means liquid covers about 3/4 of our surface. Almost all of it is freshwater. The available, almost all of it is salt water. So liquid covers about 3/4 of our surface. Almost all of it is salt water. The available fresh water for the world is 0.024% of the total water available. Groundwater contains about 30% of the world's easily accessible supply. For most of the world, it can provide up to 50%. For the US, about 25% of our water needs are supplied by groundwater. 40% of our groundwater is actually used for crop irrigation. Water distribution, though, is a serious problem. And sometimes we find that water distribution problems can vary. You've all probably heard of California having droughts. You've also equally heard of California having mudslides and floods. In areas that deal with these extreme differences with water, it makes it very hard because how do you deal with drought and then flood happening in the same place, just perhaps a few months apart? It's difficult to plan for. And this is showing you our global water supply being 40 gallons or one single bathtub. Then the fresh water available would be 1.2 fluid ounces. So that's that concept of 0.024% of the world's water being usable fresh water. It's not much. So we've talked about the water cycle. It collects water, it purifies it. The other thing the water cycle does is it distributes water all over the world. But then what do we do with that water? Because we know we use a lot of it. Well, in the US, 40% of water is used for electricity production. And no, not for hydropower like you're thinking. It's used mainly for cooling power plants. Most of it is then returned pretty quickly. It may be a little bit warmer than it was to begin with, but it is then returned into the water system. We use about 37% to irrigate our crops. 13% of the water that we use is used for the public water supply, so that means the water for us. And about 10% is used for industry, agriculture, and other types of individual water supplies. But as our population grows, as our consumption grows, we use more and more water. And that's when water conservation becomes necessary. we haven't had to worry about it necessarily all the time in Pennsylvania, but I'm sure if you think back, you might be able to remember some times where they've talked about drought. I remember being in, I think it was middle school, and there was a drought, and they were saying that we needed to be very careful with our water. We wouldn't be able to water our lawns or wash our cars outside and things like that. I remember thinking it was crazy that anybody watered their lawn to begin with because my family just didn't do that. But when things got really bad, then it was that you couldn't water your flowers or your vegetable gardens. That's terrifying. Not using water to water a vegetable garden? Why wouldn't we be able to do that? And then people started talking about, okay, well, maybe you need to make sure everybody takes short showers and things like that. But we live in an area where we may sometimes have a drought, but the water usually comes back relatively quickly, within a couple months at the worst. What about areas that have droughts all the time? What type of water conservation might be necessary then? And water conservation is kind of an interesting topic because it's the easiest way to reduce water use, while at the same time, the easiest way to increase the available water for other things. Because if I decrease my use, then I've increased the amount of water available to other people. And the reason this matters is because much of our water that we use is virtual water. Virtual water is the measure of water used to produce and deliver food and consumer products. It's a lot of water for a lot of different things. Hidden water is water that is not obvious in the finished product. We talked about your cup of coffee being 1 tub, a loaf of bread being 4 tubs of water, which is equivalent to 160 gallons of water for a loaf of bread. 11 tubs of water for a hamburger, 17 for a white t-shirt, 72 for a pair of jeans, 2,600 for a small tiny car, and 16,000 tubs of water for a house. This is hidden water. When you buy a cup of coffee, you do not get a bathtub full of water. It's just not there. It's also important that we discuss the water footprint. A water footprint is the estimate of how much water it takes each year to meet the needs of a person, a population, a country, however you set it up. We talk about this as being per capita when it's per person. And in the US, less than about 5% of our water footprint is actually water that we use for our showering, our gardening, our cooking, our actual home use. So most of the water footprint of the US is not for personal use at all. Much of it is virtual use of water. It's water that's being used elsewhere to do things for us, like making our jeans and our cups of coffee. It makes it hard for us to think about water conservation well when 95% of the water that we technically use is water we never see. And therefore, we can't conserve it if we don't know we're using it. This is a field of romaine lettuce that's being grown in Yuma, Arizona. Growing crops requires irrigation. It's a lot of water to grow lettuce because when you think about lettuce, hopefully you probably think that it's made up of a lot of water. But is Yuma, Arizona really where we want to be growing lettuce? Could we conserve water better if we grew lettuce in areas where we should be growing lettuce? Sometimes that's the question. And irrigation is very necessary to grow things in a dry area. But are there other places we could grow it that aren't as dry? When we talk about water conservation and we talk about water quantity, we also need to talk about how we alter the water cycle. Because we use water, we've talked about the fact that we use it, but as we use it, we alter how things function. We alter it by withdrawing large quantities of fresh water from streams, lakes, and aquifers. And we usually are withdrawing it faster than natural processes can replace them. We then transfer large quantities of water across land to irrigate crops, to supply water to other places. You've heard of the LA River? Well, first of all, it's not a river. It's made of concrete. There's water in it. It's not from there. There are dams that we build to keep water back, maybe to generate electricity from them. There's reservoirs that are then held behind these dams where we get the water for our needs. And then some of them are also used for hydroelectricity. This is a picture of the Hoover Dam, which was completed in 1936. It's built across the Colorado River at the border of Nevada and Arizona. The reservoir behind it is named Lake Mead. You've probably heard of it. Think about what the water cycle and the water flow would be like here. How much more water would be moving through this area if the dam didn't exist. But think of how many people this supplies water to, how much electricity it provides for us. To live the life that we live today, we might need our water to look like this. We've also altered the water cycle by clearing trees and vegetation from the land. We've filled in our wetlands for farming to build houses on. We've changed the land as it relates to where the water is. We've paved surfaces. We've blocked infiltration. And we've discovered that the more paving you do and the more blocking of infiltration you do, the more flooding you cause. Wetland soils and soils, just even in general, are better at holding on to and taking in water than blacktop will ever be. They're porous. The water is meant to go through. And soils that flood frequently have the ability to hold on to and take in more water than soils that never flood. That's why in areas where there's a lot of wetlands versus an area that's a desert, even with the same quantity of water, you don't get the flooding issues in a wetland area. Clearing the land surface, getting rid of wetlands, creating more impervious surface. These things also decrease the purification of our water. Not only does water pick up more pollutants from impervious surfaces, but the less time it spends in the system, the more polluted it becomes. We know that as we remove rainforest plants from an area, it decreases the water retention of tropical soils. But what it also does is it reduces the amount of rain in that area, because rainforest plants help to trap rain to begin with. And then they help to keep, by trapping the humidity, creating even more rain. So removal of the rainforest plants greatly alters the hydrological cycle in those areas. And then soil erosion happens, loss of soil fertility as a result. And over time, the clearing of trees and vegetation from land, the filling in of wetlands has not only changed the water cycle, but the very ecosystems themselves have been altered. The amount of water that enters them has changed. The amount of water they can keep is different. And suddenly water becomes a problem. There's also some problems with surface water issues. Reliable surface runoff is what we all want. This is the portion of the runoff from precipitation that's available for human use. In the US, in the Southwest, they currently use about 70% of their reliable surface runoff. We expect that by 2025, they'll be using closer to 90% of it. And this water is used for irrigation. There's a problem. If you use that surface water runoff, it's not going to be available to infiltrate into the ground surface. So using it in one place is kind of removing it from other places in the system. We've also created dam and reservoir systems. They do reduce the flow of our rivers. Only 21 of the world's 177 longest rivers run without a dam and reservoir system from their highest elevations to the oceans. Most of them have dams, areas with extreme withdrawal of water, and some of them with drought issues. When we look at the dam and reservoir system, it does indicate to us there's a few problems. One, evaporation is higher from reservoirs than it ever is from rivers. So a river that holds the same amount of water as a reservoir over a long period of time will hold even more water because it's decreased its evaporation. By building dam and reservoir systems, we sometimes destroy wildlife habitat. This is a big problem, huge problem, because we've flooded areas that weren't flooded to begin with. We've blocked fish migrations as well. About 1/5 or 20% of all freshwater plant and fish species are endangered or extinct. And as we create dam and reservoir systems, we change how they're able to get, or if they're able to get from one place to another. This is quite problematic. We've displaced people. The Three Gorges Dam in China is 370 miles long of a flooded area. 1,500 villages and 1.4 million people had to move for the construction of the dam. And then once we've built these systems, we need to do upkeep on them. They get filled in with sediment because as the water slows down, as it's going through the reservoir, it drops out all the sediment, which will gather on one side of the dam. You then need to pump out that sediment and mud and remove it. Otherwise, it becomes really difficult to do hydroelectric power production from these dam areas. Now, in the United States, we don't worry too much about international conflict with dam and reservoir systems, except with the Colorado and Mexico sometimes. But this is a really big deal in some areas of the Middle East. There are lots of concerns over who owns, or at least has the rights to, the waters of the Jordan, the Nile, the Tigris, and Euphrates rivers. And how much can they take? And just because the river runs through your country doesn't mean all the water in it's yours now, does it? And that's kind of the question here. And as we create a dam and reservoir system, we sometimes stress other surface water sources too. We either reduce the flow to them, divert the flow from them, or end up drawing from them as well to make up for our loss in these other ways. This is showing you the Colorado River Basin. As you can see, it covers a pretty large area of southwestern United States. The Glen Canyon Dam is what you see in the picture here that was built in 1963, and the reservoir behind it is called Lake Powell. You can see where all of the dams are on this river and where the aqueducts and canals are. We've changed greatly the flow of this river. And why does that matter? Well, the Colorado River flows 1,400 miles through 7 states. In those 1,400 miles, it goes through 14 dam and river systems, dam and reservoir systems. So that's one every 100 miles or so. Lake Mead and Lake Powell are the biggest, and they store about 80% of the water in the basin. Well, these dams and reservoirs give us low-cost water and electricity. That's good. They supply Phoenix, Las Vegas, LA, and San Diego with their public water supplies. That's important. That's 35 million people or more served by this system. 15% of the US's food production is done in this area. So it supplies a lot of irrigation water. There's hundreds of golf courses here, and all those need to be green, so you know it supplies them with water. But we remove a lot of water, and this is an area dealing with prolonged drought, so it's a problem. Since the 1960s, the Colorado River has rarely made it to the Gulf of California. There's problems in the reservoir system with evaporation, loss of water, leakage of dams, loss of water, and some concerned about their structures sometimes. and siltation problems. This is where you have that dropout of sediment causing the dams to be packed with sediment. But we also find other problems. The coastal delta and the wetlands for the Colorado River Basin are being destroyed. There's a lack of sediment at the seaward end because it's all being trapped in all of these dams. There's a lack of water flow, and we expect that there's going to be possible legal problems in the future. Well, why? Why do we keep up the system if it seems to be problematic? First of all, it's a dry region prone to drought. So if people are going to live there, they need water, and this is how we get it for them. Secondly, is that there's government subsidies that keep all of this going. And, well, then there's perhaps our greed. Maybe farming in the desert isn't a good idea. But how about golfing in the desert? Growing lawns in the desert? If you live in the desert, you should not have a lawn. End of story. You don't get to have grass because you live in the desert. I have relatives that live in Tucson, Arizona. You can't have a lawn in Tucson, Arizona. You can have cactus, but you can't have a lawn because, well, it's not from there. And some places are making laws like that where you can't have a lawn. It's a good thing. But golf courses, they use so much water. We really need to consider whether or not that's something that we need to be providing grass for. This is showing you the flow of the Colorado River and how it's changed since 1905. You can notice that it has greatly decreased overall. There are some times there where there were, as you can see, 1985 to 1990, some times of a lot of water. But overall, we've seen some pretty slow decrease in the flow of this river. And then Lake Chad, I've mentioned this one before, was one of the world's largest lakes at one point in time. It's on the border of Chad, Cameroon, Nigeria, and Niger, with 20 million people getting their drinking water from it. Since 1960, it's decreased by about 96%. Why? Well, first of all, rapid population growth. I mentioned 20 million people getting their drinking water from it. But then climate there became drier. They've gone through years of prolonged drought. And when the climate is dry, water evaporates fast. And that water was evaporating faster than it was being replaced. They had irrigation water that wasn't working well. They discovered that there was a 4 times increase in bad irrigation methods being used. And these irrigation methods were wasting a lot of water. Unfortunately, instead of the good irrigation ones being used more, it was these horrible methods of irrigation that we'll get into later that were being used. And because they were wasting a lot of water, it drained the lake, and then it started draining the rivers feeding the lake. Not surprisingly, with a loss of water, they lost a lot of their fish populations. And suddenly people were not just facing a loss of water, people also were facing a loss of food and a loss of protein. And with less protein from here, it meant, well, we have to get protein from somewhere. More water was used for irrigation, for food, and for livestock, which just gets us into a vicious cycle then of less water in the lake because now we're using it to grow more meat instead of more fish. And then there's less fish, and now we need more meat, and so forth and so on. That loss through evaporation, or that loss of evaporating water then as the water body kept getting smaller and smaller and smaller, meant there was less recharge for precipitation. So the cloud cover was decreased, which led to more evaporation and more problems. The ecosystem has become disrupted. Currently, it's still there and portions of it are still intact. But the question becomes, will the whole area collapse? If that happens, these are 20 million people who are going to become climate change refugees and are going to need to go someplace else to get water, to get food, to live. This shows you what it looks like as it shrunk. And what you'll notice is that Well, it's about 20 times larger in 1968 as it is now, or as it was in 2007. It also doesn't go into all the countries anymore, which starts making this an international policy and law concern. There's also lots of groundwater issues. Groundwater is recharged by precipitation. When we pump at a rate higher than our recharge, then, well, we're not going to be able to recharge it well. When pumping is less than recharge, everything's fine. But in the United States, we're moving water at 4 times its recharge rate on average. And most of our water is being used for irrigation, for crops. And I want to point out that bright purple area kind of in the Midwest. Most of that underlies the Ogallala Aquifer, Ogallala. The Ogallala is our massive aquifer in the middle of the country that feeds most of our farmlands with the groundwater that they need. That's an area that's seeing high groundwater overdraft. Overdraft being where you're pumping it faster than you can recharge it. Deeper aquifers are there, but it's expensive to get to them. You've got to drill down even further, and it's more expensive to pump out of them. Saudi Arabia has taken the route of going into these deep aquifers because they expect that if they don't, within 20 years, they won't have enough water. So they're kind of pioneering the work in deep aquifer extraction. But overpumping aquifers also impacts wetlands and lakes and rivers that are fed by the water that is in aquifers. It then will affect the plants and the animals that live in those impacted ecosystems. Surface systems are fed by aquifers when there's a drought and there's a decrease in surface water available. Additionally, when there is not enough groundwater, they will be losing their water to these systems. And one of the other strange issues with groundwater is subsidence. These pictures at the bottom of the screen are showing you the concept of subsidence. So as you withdraw water, the pore spaces between the sediment grains start to collapse and the ground starts to compact. As it compacts, it's going to get lower in elevation. So water is removed and the ground starts to compact upon itself. Over time, this can cause massive damage to buildings and roads. And we're seeing this happen in Mexico City, in Beijing, in Phoenix, in the San Joaquin Valley. It is a big problem. How much of a problem? Well, a problem. This is a picture from California's San Joaquin Central Valley. You can see where the land surface was in 1925 at the top of the pole and where it was in 1977 at the bottom of the pole. And subsidence has only continued since 1977. So withdrawing a lot of groundwater means a lot of subsidence. Now here, is it possible that there is some subsidence for other reasons? Yes. Yes, this is a very tectonically active area, so there could have been some subsidence from that. But some of this is directly due to groundwater removal. Salinization is an issue we've talked about a little bit already. We talked about that in Chapter 9, dealing with the soil becoming saltier as you pump groundwater, because groundwater does contain dissolved solutes. And as you pump it, these salts are going to be left on the ground surface. And groundwater is becoming saltier as that salt then recharges back into the system. And I've mentioned the Ogallala. This supplies Texas to South Dakota with their water. It's the Great Plains area. And that's where our food comes from. In the Ogallala, it provides drinking water for about 82% of its residents. But we're withdrawing water from it at 10 to 40 times its recharge rate. There are government subsidies that encourage irrigation dealing with farming substances. Some areas there cannot afford to irrigate their crops anymore. We don't know what could happen or will happen if this area is no longer able to support the agricultural industry. Hopefully, we will never find out what will happen. And this is showing you specifically the areas where we're seeing water level change in the Ogallala Aquifer. You can see some of these areas have seen a water level change of more than 150 feet. One of our other concerns with water are water transfer issues. In water transfer, we're moving water from an area that has a lot of water, a water-rich area, to a water-poor area. And in theory, this is a really good plan. Water transport, this movement of water, requires a system to move it in. Those could be aqueducts or canals, which tend to be open systems, or pipelines, which tend to be closed. In aqueducts and canals, you worry about evaporation, and in pipelines, you worry about leaking. There's a huge benefit for water transport or water transfer to where the water is going, but there's then a loss of water from where the water is taken from or from where the water would have gone to. And there can be pretty big ecosystem impacts. The California Water Project makes San Joaquin Valley, which is a dry area, into an area for food production. 3/4 of the water that's moved into this area is used for irrigation to grow alfalfa and rice. We're growing alfalfa and rice in the desert. Every time I think about this, in my head, I feel myself screaming, why are we growing rice in the desert? In what world is this a good idea? Not shockingly, a lot of the water is lost to evaporation and inefficient irrigation. The government subsidies, unfortunately, do not pay our farmers to do better irrigation. Maybe they should. And maybe that's where changes need to start, is paying people to do things better as opposed to paying them to keep doing things in a bad way. The Sacramento River is degraded. There's not enough flow anymore to flush the pollutants from the San Francisco Bay out. It threatens the fisheries. The marshes there do not have enough water that is coming in to support their ecosystems anymore. Wildlife species and the ecosystem services are declining. Mono Lake's water level has dropped 35 feet since 1941. The diversions have been halted. It's doing a lot better now, so that's good. But some of these ecosystems are either destroyed or on their way to becoming destroyed, and that's a concern. This is showing you the California State Water Project and where we're moving water. You can see the Los Angeles Aqueduct on there. I referred to that a little bit ago as the Los Angeles River or the LA River. And you can see we are moving water to areas that need it. And you can see what the LA River looks like, this aqueduct system, right here in the top in the photograph on this slide. Perhaps the biggest concern when it comes to water quantity, though, is water shortages. 1 in 7 people worldwide do not have regular access to enough water, clean water, for drinking, bathing, and cooking. 32 countries do not have enough access to regular water. 1.7 billion people do not have enough access to water. 2 million people, 80% of that 2 million younger than the age of 5, die every year from diseases due to contaminated water. You might be thinking that's a water pollution issue. Yes, it is. But it's also a water quantity issue, because when you don't have enough water, water that you do have becomes contaminated that much faster. By 2025, we expect 48 countries will be facing water shortages, with 2.7 billion people not having enough clean water to meet their daily needs. Most of these people are poor people. That makes not having enough water a justice issue. And then there's the fact that when you don't have enough water, you're probably not also going to have enough food. Drought is a big problem in these areas, but also in other areas. From 1979 to 2007, the area worldwide that was in drought tripled. By 2059, in your lifetime, we expect that up to 45% of the world's land area will be dealing with drought. And drought is a result of climate change. In 2013, there were 36 states in the United States that were facing water shortage issues. There are huge threats to human health and food production. Since 1990, 2.4 billion people have gained access to safe drinking water supplies that didn't have it before. Climate change could change this for us. And you might be wondering, what is a drought when we talk about a drought? A drought is a time period when the rainfall is below average for 21 days or more. So only 3 weeks can get you into a drought. Australia, quite a bit of it was in a drought from 2002 to 2008. Well, from 2002 until some areas, until still now, today. In 2008, they said there would be no more irrigation for the dry regions in the south. These were the areas that produced rice in Australia. This led to an increase in the price of rice 3 times normal. Drought in Australia, no more irrigation for the rice, decrease in rice supply, increase in rice 3 times, the increase in rice price. Food riots were the result in Egypt, the Philippines, and Indonesia. So suddenly, drought in Australia is causing food riots in Egypt, the Philippines, and Indonesia. If you weren't sure that drought is a human rights concern or a public health concern, you should be. There's no way we can live without water. There's literally no alternative to water. Water is more valuable than oil. Let that sink in for a moment. You can live without oil. You cannot live without water. Water is our most valuable liquid on this planet. This is showing you the areas that are dealing with varying levels of water stress, dealing with surface water use. You can see these tend to be in areas where there's a lot of poor people, and it's a problem, or where there's a lot of food production, and that's an even bigger problem. So then how do we deal with these areas that don't have a lot of water? How do we help them? This is showing you the water hotspots just for the US that are going to be facing shortages of water. Notice we're safe. The Midwest and the West are where the areas are going to be a problem. Our last thing to talk about with water quantity issues are floods. Floods are the opposite of everything I've been talking about so far. These are the opposite of droughts, and most floods are natural. Heavy rain, rapid snowmelt, hurricanes, monsoons, tsunamis, they cause floods. Now, floods are made worse by our own efforts, well, sure. When we remove trees, remove wetlands, change river flow, all of these things can lead to more floods, yes. But we expect that flooding will increase with climate change. We expect climate change will lead to more areas of drought and more areas of flood. And that's a problem because we're going to see a more unequal distribution of water around the world. Reducing flooding is possible, but requires that we preserve forests and wetlands. These are areas that store water well. It also means that we need better storage of water. Maybe more dams need to be built. But maybe we can collect water and store it differently. Maybe we can go back to things that humans have been doing for centuries, cisterns and rain barrels and tanks. We've done these all over the world for centuries and they worked. Why not go back to them? They can have just as small levels of evaporation, maybe even less if we put lids on them, than our reservoirs have. So a good way to deal with areas that are going to be seeing a lot of flooding is finding a way to hold on to and keep that water so that we can use it in other times or transport it to other areas. On Wednesday, we're going to pick up with the concept of what do we do about all of this.